Hey, how are you?
I'm good. How are you?
I'm doing okay.
Uh-huh.
Uh, Second.
Mm-hmm.
All right. How are you doing?
I'm good, thank you.
It's good.
Hmm?
Cool. Sharing the screen right now. Okay.
Are you using Windows now?
Oh yeah. Using my gaming PC right now.
Oh, nice. What have you been
Yeah.
playing? I
What
see,
happened?
see CSGO and stuff.
Yeah, I've been doing CS:GO, Diablo,
Mm-hmm.
uh, Doom, Street Fighter.
Cool.
Yeah. Planning to get Tekken soon, I think.
Mm-hmm.
What have you been playing recently?
Mass Effect,
Oh,
uh,
nice.
Legendary Edition.
Okay.
It's like the same games, but sort
Remastered. Yeah.
of, and Insurgency like usual. I mean, I haven't played Insurgency since like August, but that's just always been my default game.
Yeah.
Mm-hmm. What gaming card do you have?
I have an Asus GeForce RTX 3070 Ti.
Oh, nice.
Yeah,
Yeah. I had a 280 and then it died and then I got a 3090 Ti.
nice. Yeah, and my processor is the CPU is Intel i9
Hmm.
uh 13 900K.
What was that?
Uh what is it? 13,900K, something like that.
Okay.
So,
Hmm.
yeah,
Cool.
not bad. Want to do some upgrades to the cooler and stuff eventually, but
Hmm. Yeah, I had to do that because I have like a Threadripper 2950X and
uh,
it's not the same size as regular PC like CPUs. Like it's not that square.
yeah,
Like a long rectangle. And I didn't realize that, when I first built it, that the cooler that I was using was just for the small size CPU. So like for like 4 or 5 years, um I was using a really good cooler, like a liquid cooler, like Kraken
hmm,
X62, but it was only touching like you know, maybe like 75% of the CPU. So I had to get um so I got a new one that's specially made for the socket of my CPU, which is really wide,
yeah,
and it's been pretty good. So
that's good.
Mhm.
Yeah, that's really good.
You built it like the desktop, or did you get it like pre-made or whatever?
So it was built, but I had a friend, when I took my last class in college, he's a computer science major. He just
Yeah.
buys a whole bunch of parts
Yep, yep.
and stuff for whenever he needs them, but he had excess.
Yeah.
And he just told me I just needed to get the case and the graphics card because he had everything else.
Yep.
So he gave me the i9
Hmm.
Intel and stuff and the cooler and everything. So I pretty much just paid 750 for the graphics card and then like 115 for the case.
Yeah, yeah,
That was it. But yeah.
yeah. I also have like RAM, like two of my RAM sticks like stopped working, so um because I had 64 gigs of RAM, but now I have 32.
Hmm.
But but yeah, it's what happens. I mean, I built this back in like around this time, 2019.
Hmm.
My computer's basically on for like at least 12 hours a day every day for like 4 or 5 years. So eventually something.
Yeah, stuff was gonna die out.
Mhm. Yeah.
So
It
All
was
right.
most annoying when the graphics card died out because I had to get the 3090 Ti at like whatever price was available at the time. I mean, it's still cheaper, I guess, by like maybe or like roughly the same price as it is now,
Mm-hmm.
which is weird because if you look up like benchmarks, there are several cards that perform better that are less expensive than the 3090 Ti. But the
Mm-hmm.
3090 Ti just has a lot more virtual memory, so I think that plays a role in some things. But okay, awesome. So cool. Uh your health's okay, things going well?
Yeah, it's going as well as it can, I guess.
Yeah.
Just finished getting off of the steroids like a week or two ago.
Yeah, let me go back. All right, so how's this content diagnostic going?
It's going all right. I had finished it. But I got like a 50 on it, so which is not bad, I guess, for as much of the questions there are. But gotta go over what's wrong.
Yep.
So I understand why that's wrong.
Hmm.
Okay. I want to go over what 1s2, 2s2, and all this stuff is. It's always been a weak point for me in chemistry.
Yep. So why don't you open up that periodic table? So this is how you can do this. So the first two columns here, we can call the S block.
Mm-hmm.
And then these last couple here, we can call the P block. And then
Okay.
these transition metals called the D block.
Mm-hmm.
So for any uh for any element, we can figure out what the electron configuration is. Now the rows go down like 1, 2, 3, 4, 5, 6, 7. But once we do anything that's a d orbital, we just subtract that number by 1. So so okay, why don't you give me like an element, like pick any element, and I'll show you how to do it.
Um, I don't know, palladium.
All right. Where is it here? Okay. So this is what we do. So first of all, um, to make it like shorter, we will include the last noble gas
Mm-hmm.
before it. So we can write like in brackets krypton.
Mm-hmm.
And then from there we can move forward. So then we see that we're at the fifth row.
Mm-hmm.
The first two elements here
Mm-hmm.
will be the S elements. So like
So 5s2 would be that.
exactly.
Okay.
And
And
then for
then
the D,
5, 1, 2, 3, 4, 5, 6, 5d7.
I think this is 8.
Oh, 8. Okay.
Yeah. But when we do D orbitals, we just subtract that number, the row number by 1. So it will be 4D7.
Mm, okay. Understood.
Mm-hmm. So why don't you tell me what it would be for sulfur?
For sulfur. Okay. Um,
So start with the like
3s2.
most recent noble gas.
Oh, start with the most recent one. Okay, so neon. Um, and then 3s2,
Mhm.
and then P.
Uh-huh. It would
Uh,
be
I mean 2p.
so,
Um,
so you
4.
subtract only for the D.
Oh, for only D, so everything else stay the same for S and P. Okay, so then 3p 4.
Good. So what I mean about the noble gas is that's just a shorter way of writing it because otherwise you would have to write the entire thing. So for instance, if I wanted to do neon itself, right? That would
Yeah.
oh, and then this helium here is a bit of an exception because it counts as an S.
Okay.
So for if I wanted to do neon, it would be so the 1s, 1 for the hydrogen, 1s, 2 for the helium. So it'll be 1s2 and 2s2 for lithium and beryllium, so 2s2. And then 2p, 1, 2, 3, 4, 5, 6, 2p6. So that's
And that's the electron configuration of neon.
yeah. Now,
Okay.
when we do, later elements and stuff, it would be too long. It would take too long to write all of it out. So that's why we start
Just use
off
the
with,
next noble gas and then go as far as
yeah,
possible.
yeah, yeah. Now, there's two exceptions here. The
Okay.
exceptions are so in the so one of the exceptions is this block here. Maybe I'll use like a lighter green. So this block and this one. So what I mean by exceptions is that anything in this row we call half we call it half filled.
Mm-hmm.
So because what that so like for instance like S like the S orbital, it's one orbital that can contain oppositely uh two electrons with opposite spin, right?
Yeah.
And then the P orbital, there's three of them, right? Because there's like a PX, Y, PZ. And now for the D, there's five for the D. Okay.
Okay.
Now for for let's say I forgot what the CR was. What was the CR? Chromium, I think.
Yeah, it should be chromium.
So for the chromium, right? So this is what I mean. So let's do chromium. So, we like I can do like okay, argon first, the most recent noble gas.
Yeah, and then two, I think
Yeah.
4s2.
And yeah, so then it would be the 4s2 and then 1, 2, 3, 4. So 3d4.
4.
But when you draw it, so I'm going to draw the 4s2 at the 3d4 in the orbitals here. So it would be like, so the first electron in S would, let's say, have a spin up. The next one would have a spin down.
Mm-hmm.
We're not in P's yet. And then for the D's, so what you do is you put electrons in each orbital first, and then if you run out of room, you put the down electron. So like this would be like 1, 2, 3, 4.
Oh, okay.
All right. Now, this is an exception. This entire column is an exception because what you want to have happen is you want to have the d orbital half filled.
Yeah.
So what that means is you're going to take an electron away from that s orbital.
Oh, and you're gonna put the up
Yeah.
onto the D.
This way you have the d orbitals half filled. So this turns into, so it's still the argon, but then it's going to be 4s1, 3d5.
So you basically take an electron away from the s orbital and you.
Yep. Yeah. And yeah, that number indicates like its location. Like if it's a higher number, it's further out from the nucleus. So whenever you have like if you have to have if you have to have an electron leave an orbital, it'll leave from the 4 rather than the 3D. Now, there's another exception
Mm-hmm.
that I'll show you. So
Oh, sorry.
huh? Yeah, so the other exception, oh yeah.
Yep, I moved it. Sorry
Mhm.
about that.
So yeah, the other exception is here where you want it to be fully filled. So for example, so like yeah, if I did again like S, the three P's that we're gonna skip, and then 1, 2, 3, 4, 5 D's. So let's say we have um copper, right?
Mm-hmm.
So um so this would be so like yeah, so we'll start off with the argon, and then you'd have 4s2, so this again. And
Mm-hmm.
there's 9 electrons in the copper. I mean
Mm-hmm.
the d orbitals. So this would be 1, 2, 3, 4, 5, and then you would start back at the first one going down 6, 7, 8, 9, right?
Oh, so you just keep taking from P in that instance, so you keep filling the D?
Oh, so we don't have any p yet?
Um, okay, go over that again. I'm a little confused.
Yeah, yeah. So the reason we're not going over P yet is because that comes into play once we go in this area, the P block there.
Where? P block where? Oh, that. Oh, because we're using argon and then we're going to copper.
Yep.
Got it. So we don't even touch P. We're just using S.
Mm-hmm. Yeah.
Okay.
So now we have this thing that I drew over here on the bottom left.
Yeah, S2, and then it would be D, what is it? 9?
So yeah, this would be 4s. Well, look. So this would be
Yeah, 4S2, D, 3D9.
yeah.
Yeah.
Now this is the column where the other exception happens where it's fully filled. So you're gonna have again an electron leave the S.
And you're gonna fill it to completely fill the d orbital.
Yeah, so now this becomes argon 4s1 3d10. So those are the exceptions.
All right. And that's when you're drawing it, right?
When you say drawing it,
Like when you have to make a diagram for it, I guess, or like pick out the best diagram for it.
so the diagram like that I drew down here, uh,
Yeah.
just to show you like why it happens. But they could ask you like what the electron configuration is of like molybdenum or like silver or gold. Um, and you should be able to tell without needing to draw that you're going to take an electron from the s orbital and you're going to put it into the d one, just because you want the this column here, the half to be half filled, meaning you want the d orbitals to be completely half filled, and then this column you want the d orbitals to be fully filled.
Got it.
Mhm. So okay, those are the exceptions. Now this question is asking about an oxide ion, right? So
Mhm.
why don't we start off by writing the electron configuration for oxygen and um and yeah, from the start. So like yeah, so what would it be for oxygen?
All right, 1 second.
Just gonna make some
Okay. So for oxygen?
yeah. I'm gonna just
Okay, so if we're doing that, then we're gonna go 1s. What the hell is that?
I just put some white space there so I could write on it.
Oh,
Hmm.
I can draw on it.
Hmm.
Okay, got it. Uh, so we have 1s1. there, 1s2. We can count helium as 2, right? As 1s2?
Yep.
Okay. So 1s2, 2s2,
Mhm.
and then we have 2p4.
Mhm. Good. So that's for oxygen.
Mm-hmm.
Now for the oxide ion, right?
Mm-hmm.
What happens there? Like what is an oxide ion?
Wouldn't that be just O2?
Yeah, 2 minus, right?
Yeah, O2 minus. Yeah.
So oxygen would be gaining 2 electrons, right?
Yeah.
So uh
Oh, so if oxygen's gaining 2 electrons, then we're gonna make it 2p6 here.
yeah, and where is it getting it from?
Um,
Well, it could be just anything else. So
yeah.
yeah. So
Okay.
it's not going to be getting it from its own, thing. So yeah, that would be the oxide ion right there.
All right, so 1s2, 2s2, 2p6.
Mhm.
Got it.
And you can kind of see that with everything else. Like for instance, like chlorine over here,
Yes.
like that would be like neon and then 3s2, 3p7, right? Oh,
Yeah.
what am I talking about? 3p4, right?
Yes.
And to turn into an ion, like anything in general, in order for it to turn into an ion, it would have to have the same electron configuration as the nearest um, noble gas. So that's why for like oxygen, right, it can gain an electron to be like fluorine, and then it can gain another electron to be like neon, right?
Got it.
And then for chlorine, it can gain 1 electron to be like argon. So for the chlorine, the chloride ion, it would be this. Or sorry,
Mhm.
I put 4 before, which is wrong, but this is 5
Okay.
because it's 1, 2, 3, 4, 5, right?
Yeah.
And then to be that, so that's for chlorine, and then for the chloride ion,
This is gonna turn into a 6.
yep. 3s2, 3p6. Because then that's the max amount you can put in the six in the p orbital. Now, for let's say something like magnesium here, right?
Okay.
So like for this, we still have to think about how we can get to like the nearest noble gas. So either we add 1, 2, 3, 4, 5, 6 electrons to become like argon, or we lose 1, 2 electrons to be like neon. And whichever one is easier, that's what it will do. So if we have magnesium, that would be
2 plus.
neon with 3s2, right?
Mm-hmm.
And then magnesium ion would be 2 plus.
Yeah.
That would
So we
just
just have
be
neon.
neon, right? Yeah.
Got it.
So yeah, that's how you can take a look at for any element, right? You can take a look at the periodic table and then figure out what its electron configuration is. And there's the exceptions with the half-filled D and the full-filled D.
Mm-hmm.
And the exception with D in general, where the number goes down by 1. Um, and then also, in order to create an ion, you want it to have the same electron configuration as the nearest noble gas.
All right.
So why don't you tell me what it would be for selenium?
Selenium would be 2 minus, right?
Oh, just with
Mm.
the selenium atom.
Oh, okay. I'll do it here, okay?
Hmm?
Selenium, so we're gonna go argon.
Hmm?
Sorry, I'm not used to this.
Yes.
Uh, 4s2.
So this time it actually goes through the D.
Yeah, so D, and then there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10.
Mm-hmm.
And then we have 4p4.
Mm-hmm. Good. And then if it turned into an ion, it would just be
Yeah, if it turned into this, then we turn that into 5.
so.
Whereas selenium can only be positively charged?
Well, let's think about how it can get to its nearest noble gas, right?
Mm-hmm.
So what can it do? Well, what's its nearest noble gas?
Um, Argon.
So
Or krypton, sorry.
because it can either lose 1, 2,
Oh,
3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14,
or it
15,
can gain 2 electrons.
16. It can lose 16 to be like argon, or
Uh-huh.
it can gain 2 to be like krypton.
So if we make it an ion, it would be 2 minus, so then this turns into 6.
Exactly.
Got it.
Yeah. And if you wanted to see like what the like the P would look like, so it would be like 1, 2, 3, 4, 5, 6.
Yeah.
Yeah.
Okay, good.
Mhm.
Awesome. Awesome. Awesome.
Mhm.
All right, so let me close that up.
Yeah. Did you want to take a screenshot or whatever?
Oh
Or
yeah, me.
when I put the video up, you can take it from that also. But yeah, if you want, you could take it here.
Yeah, I'll just take it here. It's still the whiteboard. Okay, cool.
So clear.
All right, awesome.
Mhm. Yeah. So see how this one would be that one.
Yeah,
Yep. So you chose the correct one for oxygen.
yeah.
Mhm.
Uh,
So
yeah, that would make the most sense.
yeah, well, so okay. What can you tell me about this? Because this is its own kind of thing.
Okay. Well, if we're talking about ionic radius, we're talking about like how many electrons it would have, right? If we're
So
choosing the largest.
so all of these will turn out to have the same number of electrons.
Okay.
Like I can even show you if you open up the periodic table and just like move it a little to the left so we can kind of see the, or maybe you can't do that, but
Let me open up the periodic table online. Hold on.
okay. Mhm.
Okay. There we go. Let
Yeah,
me
so for the
get separate tab.
mhm. Yeah.
Cool. All right.
So for like this nitride ion here, that
Uh-huh.
would be nitrogen, and then it would gain 1, 2, 3. So it'll have an electron configuration equal to neon.
Mm-hmm.
Oxygen gains 1, 2,
Two to
also
be
equal to
neon.
neon. Sodium loses 1,
This would become neon. And then
magnesium loses
magnesium
2.
loses 2 to become neon.
Yeah, so they all have the same electron configuration. So what we do here is thinking about ionic radius. So let's say, for instance, like if I have a one proton in the nucleus and then one electron, around it, this will have a certain like size, right?
Yeah.
Okay. Now, let's say that, well, okay, let me start off with two of these and then two electrons here. So this will have a certain size, right? Now, let's say I got rid of an electron. What would happen? So what would happen is that the nucleus with its two protons that previously was pulling like the two electrons towards itself.
Hmm.
Now it only has to pull one electron towards itself. Now, since it only has to pull one electron towards itself, it can pull it closer to itself.
Okay.
Okay. So for an atom or an atomic radius, this would be what type of ion if we lost an electron? Would it be an anion or a cation?
Um, anion.
If you lose an electron,
Oh no, become a cation, sorry.
because it would be positively charged, right?
Yeah.
So the cation size, since you're losing an electron, the nucleus can pull whatever electrons remain closer to itself, which would result in a smaller size.
Mm-hmm.
So for any given atom, its cation form will be smaller.
Okay.
Now, let's imagine the opposite. Let's imagine that we have, so this is again back to its normal state, but now let's say we have three electrons. So
Okay.
you have an extra electron here. So the two protons in the nucleus won't be able to pull it as close to itself because it has to spread its pull across three electrons instead of two, like normal.
Mm-hmm.
So this would result in a larger size.
Okay.
So the anion, so for any given atom, right, the cation form will be smaller and the anion form will be larger.
Okay.
Okay. So that's why for this question, all of these choices they have. So a common mistake that people can make is, generally speaking, atomic radius. What is the periodic trend for that?
The atomic radius.
Mhm.
What do you mean periodic trend?
So you know how there's the periodic trends, like if you go this way,
Uh-huh.
like if you go this way,
Yeah.
negativity goes up, right? Electron affinity goes up, ionization energy goes up, right?
Okay.
You go up into the right.
Yeah.
Now, if you do the opposite, which is down and to the left, only one periodic trend goes up, and that's atomic radius.
Yeah.
Okay. So
Okay.
a common mistake for this question is if people didn't see the ion part,
Mm-hmm.
because if people did, so if it was just the atom, which would have the largest atomic radius?
By magnesium.
Well, it goes, atomic radius goes up as you go to the left and down.
Oh, oh. As you go to the left and down tire. So I guess if people weren't really looking at the yeah.
So left and down, right? So is there
Yeah.
something left of this?
Oh, sodium.
Yep. So if it was just asking for the largest atomic radius, the answer would be sodium, right?
Mm-hmm.
And that's why 30% chose sodium.
But it was asking for the largest ionic radius. So if we're
Right.
talking about ionization energy and everything, it's going up. So
So the largest ionic radius will be whichever is the most anionic.
yeah,
And
got it.
that would be this. Okay.
Okay. makes sense.
Mm-hmm. Okay.
Um, which of the following statements regarding alkali metals correct?
Yeah,
Oh,
so this is just like a content thing to know. So the alkali metals are this, first column. The alkali
yeah, they're hydrogen
metals are in
in
the
the
second
1A.
one.
Yeah,
And yeah, just something to know is that if they react with water, because
yeah, they oxidize.
you've heard about like if you dropped pure sodium in water, it would like explode or whatever, right?
Yeah,
Yeah, that's because it will form hydroxides. So that's also why you see like sodium hydroxide, right? Potassium hydroxide,
yeah,
stuff like that.
and
So
then yeah,
mhm,
got it.
yeah.
And aren't those also extremely basic?
Yeah, because they, would dissociate into
Yeah,
that, and the hydroxide ion is extremely basic. Yeah.
yeah.
Hmm.
All right. The second greatest ionization energy.
Oh,
So
great. Second ionization.
now that I,
So it's asking for greatest second ionization
yeah,
energy.
not the greatest. The greatest would be what would it be? Here, if we're actually going.
So this would be a trend that would go up and to the right.
Yeah. So where's beryllium? What the hell? Beryllium should be
Here.
oh right here. Yeah, yeah. So it's, then the greatest one is beryllium, no?
So that would be the greatest ionization energy.
Yeah, yeah. I'm saying the second greatest would be lithium, but I'm saying the
So,
greatest one
so
would be
be
beryllium, right?
careful there because it's not asking second greatest. It's asking greatest second.
Oh,
So, so okay. First of all, beryllium would have the greatest like first ionization energy. So again, that's why 27% chose that.
okay.
Greatest second ionization energy. So okay. For let's see if you could bring up like a more simple periodic table because it's kind of hard for me to write on that one.
Okay.
Like just one that's like white or something. You can go to images up left. Yeah. And yeah, like something like that's fine.
There we go.
Yeah. Okay. So okay. Second ionization energy. So let's think about what ionization energy is, right?
Oh,
So
what the hell?
hmm,
Sorry.
let me see if I could
Ah, okay.
find an easy one for you. Okay, I think this would work. Um oh yeah, so just if you go down a little bit in your
Okay.
image search,
Yeah, I'm trying to. Ah,
yeah,
here we go.
like one that's white, yeah.
There we go.
Okay, so yeah, make it a little bigger. Yeah, okay. So let's think about what ionization energy is, right? So
Yeah.
ionization energy is the energy it takes to remove the outermost electron to give you your um, noble gas equivalent, right?
Yeah.
So, for instance, for like sodium, right, it
Hmm.
would have the ionization energy would be the energy it takes to remove the outermost electron. And if you remove the outermost electron, it would have the same electron configuration as neon. So for instance, for sodium, I'm just going to write, so this is neon and then 3s1, right?
Hmm.
So the ionization energy is the energy it takes to remove this electron to give it the same electron configuration as neon, right?
Hmm.
And it would be super stable there. So what that means is that it doesn't take that much energy to remove this outermost electron, but once it turns into neon, which by the way is 1s2, 2s2, 2p6,
Mm-hmm.
right? To remove, so the second ionization energy is to remove a second electron.
Got it.
Now, if the first ionization energy removes that first electron and it gives you the same configuration as neon, it's super stable like that, right?
Mm-hmm.
So if you wanted to remove an electron from this, it would be a super, super high number because it's already stable like that.
Yeah.
Okay. So for neon, right? I'm sorry, for sodium, right? Its first ionization energy, so I'll write it second ionization energy is significantly larger than its first ionization energy.
Okay.
Okay. So let's compare that with magnesium, right? So magnesium would be like neon, but 3s2, right?
Mm-hmm.
So if you remove the first electron from magnesium, it would be 3s1, right? But you want it to have the same electron configuration as neon. So you want to remove the second electron to give you the same thing as neon. So,
Okay.
so that means that magnesium will have a lower second ionization energy compared to the first. Okay.
Okay.
So this will then hold true for, or this pattern will hold true for lithium and beryllium, right? So if we compare lithium and beryllium, so both of these are already above sodium and magnesium, right?
Mm-hmm.
And if it's above, either if it's above or if it's to the right? Both of those would mean that it would have a higher first ionization energy. So right away, we know that sodium and magnesium should be out because lithium and beryllium already have larger first ionization energies. So the second ionization energy should be larger also.
Mm-hmm.
So now let's compare the two. So like beryllium, right? Its first ionization energy would remove an electron to make it the same electron configuration as lithium, but it wants to be like helium, so it would lose another electron to be like helium. Okay. So that would
Okay.
be like it would want to have a low second ionization energy, right?
Yeah.
Because it wants to have, in order for beryllium, magnesium, calcium, all this stuff in this column, right? In order for it to turn into, in order for it to have the same electron configuration as the nearest noble gas, it would have to lose two electrons, right?
Yeah.
And if it loses two electrons, the first ionization energy is the energy it takes to remove the first electron. Second is the energy it takes to remove the second one. So if these elements want two electrons to be removed, that second ionization energy is not going to be very high. Okay.
Okay.
Now let's compare it to lithium, right? If lithium
Mm-hmm.
loses one electron, it has the same electron configuration as what?
Helium.
Mm-hmm. And it
Yeah.
wants to be helium.
Yeah.
So if you removed a second electron from helium, right, it won't be stable, right?
Yeah.
So its second ionization energy would be much, much larger, just like it is for sodium.
Okay.
So you want to think about, so yeah, so first of all, you just want to understand that ionization energy is the energy it takes to remove. So let's talk first. So whenever they say ionization energy, they mean first ionization energy, which
Okay.
means taking out like, or the energy it takes to remove the outermost, like one outermost electron, right? But second ionization energy is the energy it takes to remove the second outermost electron. Okay.
Okay.
So if you have something like, so lithium turns into lithium plus, right? Sodium turns into sodium plus.
Mhm.
Potassium turns into potassium plus. So everything in this column, in order for it to turn into an ion, it will lose just one electron.
Yeah.
Because if you wanted to remove its second electron, it doesn't want to do that. Because if it loses one electron, it's super stable. So if you want to remove a second electron, it's not going to be stable. So its second ionization energy will be large because it doesn't want to do that.
All right, got it.
So like, why don't you talk to me about barium here?
So for barium, it would be xenon. So
Mhm.
the closest to get to xenon will be 2 plus.
Yep. So it would have to lose two electrons, right?
Yeah.
So that means that its second ionization energy won't be that high.
As it won't be as high as if it was cesium.
Correct. Because cesium, to turn into, its most stable form, will lose how many electrons?
1.
One, right? And then it would have the same configuration as xenon,
Yeah.
and it wants to be there. So if you wanted to remove another one to have it have the same electron configuration as iodine, it
Hmm.
doesn't want to do that. So its second ionization energy will be super high.
Got it. Okay.
Okay. So, so this one we have, so if you wanted to compare sodium and magnesium, right? Sodium will have the highest or higher second ionization energy.
Hmm.
But then we have lithium and beryllium, which are above sodium and magnesium. So they will already start off with a larger first ionization energy in general. And then you would just use the one that would turn into the +1 ion. So that would be.
Okay.
Mhm.
Got it. All right. Cool, cool.
Mhm.
Um,
Oh, okay. So
eh, okay.
yeah. So okay, you got, so yeah, it's not an ion. I mean, sorry, it's not a metal. So you got that part right. But I guess it's just the period.
Oh, it was supposed to be period 5.
Yep.
I was probably counting too fast.
Hmm.
All right. Sucrose, commonly known as table sugar, is disaccharide composed of glucose and fructose. Which molecular mass of sucrose? Yeah, that's fine.
Hmm.
In order for an airbag to inflate, sodium azide is decomposed according to the balance reaction below. Oh
Hmm.
yeah, that's supposed to be like this little thing, and it's activated by heat, right? That they put in the car, and then it like bursts.
Oh
So,
yeah, I'm
yeah,
not
it's like
sure about that part, but yeah, okay. So we have a balanced reaction here. And so this is a very like kind of typical type of, problem, like stoichiometry problem. So like basically, so we have the balanced reaction, all right, which means like for instance, 2 moles of NaN3 would produce 2 moles of sodium, 3 moles of N2, right?
hmm.
So what they're telling us is, what if instead of the 3 moles of N2, we wanted 2.25 moles of N2,
Yeah.
right? Now that would change the amount of moles that we need of NaN3, right?
Hmm.
So we would need to figure that out. And they're asking how many grams of sodium azide, which is this, must be stored in an airbag. So what we want to use is a conversion factor. And
Okay.
what conversion factor should we use to go from moles to grams and vice versa?
Um,
Mhm.
Well, if we want to go from moles to grams, we would just go uh
Mhm.
what's the one that has grams per mole?
Molar
Uh
mass, yeah.
huh?
Molar mass.
Yeah, molar mass. Yeah.
Good, good, good. Okay. So let's do this, right? So okay, so we know that they're asking for 2.25 moles of N2 gas, right?
Mm-hmm.
Now we take the balanced reaction to figure out like a mole ratio, right? So in the balanced reaction, we have 3 moles of N2, right?
Yeah.
Now, if we had 3 moles of N2, how many moles of sodium azide would we need?
Well, it says two, so
Right? So 2 moles of sodium azide. So this calculation, right, would
mm-hmm.
give us the number of moles of sodium azide that we need,
Okay.
right? Um, Now I don't know if I should do this separately to show you that it would give you like the moles of like however many moles of sodium azide you would need, but I guess yeah, we could do it separately. So okay, so like let's figure that out. So if we did this calculation here, uh
Mm-hmm.
yeah, how would we be able to do this?
Well, we would do whatever's in here first, and then just multiply this by what's in here, and then get the amount of moles. Right.
Okay, so tell me what you would do.
2/3, which is the same as what is uh 33%, 33.3%. So
It would be like 66%, but
oh, sorry, 66.
easier-
Yeah, yeah. I was going by three.
I think what would be easier is why don't we just do 2.25 times 2 first?
Mm-hmm.
So that would
Okay,
be
so that would be
4.5.
5.
Well, 4.5?
Oh, 2.5. Sorry, no,
Yeah,
2.5. Yeah.
2.25. And then we can divide this by 3.
Okay.
Um, which could be a little confusing. So maybe I would do so okay, I can show you like kind of like a trick that is so for instance, 4.5 is the same thing as 9/2, right?
Mm-hmm.
So instead of the 4.5, I would write 9/2. And since we're dividing it by 3, I would multiply it by the reciprocal of 3
Okay.
to get this, right? And now
Okay.
things can cancel. The 3 can go into 9
Two times,
times.
and then the two
So
can
this
go
would
into one
just
one
be,
time.
yep, and this would just be 3/2, right?
Yeah.
Which is what as a decimal?
Should be 1.25, right? Or 1.5.
1.5, right?
Yeah.
So okay, so this can just be 3/2 or 1.5. And you see how the moles of N2 should cancel? So this
Yeah.
would be moles of NaN,
ESI.
right?
Mm-hmm.
So okay, so we have our number of moles. So that's the first step. And we figured that out by using the balanced reaction. So now,
Yeah, so now all we need to do is get the amount of grams that sodium azide is by itself, and then we just do it by 1.5.
yeah, so we can write, for instance, 1.5 moles NaN3, and then we can multiply it by the gram formula mass or the molar mass. So that would be the mass of 1 mole of sodium azide, right?
Yeah.
So yeah, let's figure that out. So how do we find that out?
Well, we just get how many grams uh
From the
per
period.
mole that Na is by itself.
Yep. So well NaN3, right?
Yeah.
So that'll be sodium, which is like what 22,
Yeah.
23.
Sodium, yeah, is 22.9 or 23. You
Mm-hmm.
just put and then N2 would just be 14.
14 times N3, right? So
Yeah, yeah, and three,
times
so
3.
it'd be 14 times 3, which
So
is what
mhm.
is that? 32?
So I would do like 15
No,
times
42.
3.
Huh?
Yeah, I would do that. Yeah,
Yeah.
so I feel like 15 times 3, right? Because that
Hmm.
15 times 2 would be 30, plus another 15 would be 45, and then sure you can subtract 3 from that.
Yeah, so then that's
32
42, and that's
plus 23.
45, 65.
Yep.
So
So
then 65,
mhm.
then just times 65 by a half, and then you get 32.5, so
Yeah.
97.5.
So let's move this periodic table so we can go back to what I was writing. Yeah, so here we would put 65 grams of NaN3, right?
Yeah, and then the moles cancel out,
Yep.
and then you just times 1.5 by 65, and you'll get 97.5.
Yep. So this would be so I guess we could also do like 3 over 2 times 65. And maybe I'll just make that 64. 2 goes into 64 32 times. 3 times 32, right? Would be like 90.
96.
So 90
Closest answer is 97.5 then.
grams of NaN3.
Yeah.
So, so yeah, that's how we would do this. So you see how what we do is we take the amount of moles of nitrogen gas that they give us, and
Hmm.
we use the balanced reaction to create like uh the proportion, right? Because like for every 3 moles of N2, there's 2 moles of NaN3. So for 2.25 moles of N2, we would need, when we do the math, like the 1.5 moles of NaN3, right? And then we use the molar mass to figure out the mass of that amount.
Got it.
So yeah, this is a very kind of typical stoichiometry question. So you should, be very, very comfortable with doing this type of um question as well. Yeah, so here's like another one.
Hmm.
Why don't you walk me through this one?
Uh, okay, so let me get the annotation. All right, so what is that we need? Aluminum required to produce 50 kilograms. Okay, 0.50.
That out.
All right. Given the amounts. Okay, so seems like they don't really give us anything else than just kilograms. So we can just use the grams per mole again,
Yep.
and then just convert grams to kilograms afterwards.
Well,
So,
we want to, so remember the grams per mole, right? That's
mhm,
the conversion factor that lets us, if we have moles, we can find the grams, the new grams. If
yeah,
you find the grams, you can find the new moles.
okay.
So what we would do, so like how I would set this up, right,
Mhm.
is I would put like, you know, that says 0.5 kilograms, right?
Yeah.
So maybe I would just turn that in. So how many grams would that be?
0.5 kilograms should be like what? Like close to, no, Jesus. Let me see.
Well, wait. You don't want to look it up though,
Oh yeah.
because you
I'm just because I was I was saying 50 or 500 in my head, so
yeah, yeah. So like 1 kilogram would be half,
is 1,000 grams. Yeah, that was
and then zero point 0.5 would be half of that, right?
yeah.
So
So
500
500
grams.
kilogram, 500 grams.
Mhm. So okay, we got
So
500 grams of iron, right? And what do we do?
um,
Because what do we want to turn it into?
we wanted to turn it into the number of grams of aluminum required.
Oh,
So
like ultimately, right? But in like
yeah,
the first step,
yeah.
what
So
do we want to do in the first step though?
so if we want to make 500 grams of Fe
Mhm.
and we need the aluminum required, then we would just put like the number of moles of aluminum.
So let's not think about the aluminum yet. Let's just, like how we did the previous problem in 2 steps. Let's do it in 2 steps. And then I'll show you how to do it in 1 step, but let's make sure we can do it in 2 steps.
Okay, so Fe is should be
Here
oh Jesus.
in the middle, because it's a note, it's a
There we
type.
go. Yes. 55.8. So 56.
Okay, so
So
that's how many grams are in 1 mole, right?
mm-hmm.
So that would mean, oh yeah, we could. So we would put on the bottom, right? It was like what, 56?
Yeah, 56 grams per mole.
And then 1 mole of Fe on top, right?
Yeah, Fe on top, and then that'll cancel the grams over here so we can get the amount of moles necessary.
Mhm. Good.
So 50 times 5 would be 500. You could say approximately 5.
Well, let's see, right? Like, because we're doing like how many times 56 goes into 500.
Yeah.
So it would be kind of like a little less than 10.
Oh,
Because
50 times 10, sorry.
if we had like 50 grams here, like it would go into the 510 times, right?
Yeah.
Um, but yeah, it should be a little less than 10. So let's say, I don't know, maybe 9 or something. To actually do it, I can show you that too. So 500, this is how I would actually do the math, fit over 56. So
Mm-hmm.
I don't think like long division is helpful or anything like that. I think it's mostly helpful to just make uh,
Everything into
a
a
fraction
fraction.
and then you just simplify it, right? So first I would ask myself, okay, uh like what's the number that can go into both of these?
Mm-hmm.
So I mean when you say the 56, does anything come to mind? Like or maybe we could just do, let's just see how many times 5 goes into
Oh,
each.
well, eight goes into
7.
56
Uh-huh.
7 times.
Yeah. But I think it would be harder to do that into the 500, but let's try something like if this was 55, right? So 5 goes
Mhm.
into 55 11 times.
Yeah.
5 goes into 500, so it goes into that 100 times, right?
Yeah.
And then it would just be like 100 over 11.
Which gives you approximately 9.
Yeah. So let's say 9 moles of iron. So okay, we got the we got the moles of iron. Um Now what do we do?
So now that we have the 9 moles of iron, we can make a whole new thing, right?
Hmm?
Um, and do 9 moles of Fe, make the bracket again. Should be 1 mole of aluminum, right?
Oh yeah. So now is when when you when you have the moles, that's when you use the balanced chemical reaction.
Mm-hmm.
So we know for every 2 moles of 2 moles of iron, how many moles of aluminum?
We have 2
Good. So 2 moles of iron, 2 moles,
moles of aluminum.
and this would give us the number of moles of aluminum, but we want to figure out the number of like the grams of aluminum. So then we can just add in like another calculation for that. So what would we do here?
Mm, well, we get the number. Yeah, cancel those out. So now they have 2 moles
Mhm.
uh aluminum. We could use the number.
So now we want to go from moles of aluminum to mass of aluminum, right?
Yeah, so 26.9, so 27.
Yep. So where would we put what?
27 will go down here.
Well, 27
Right.
is grams, right?
Yeah.
And you want that in your answer?
Okay, so 27 G,
Yep, yep.
right? AL. Uh,
And then this would be 1 mole
yeah,
of
1 mole
A.
AL.
So you see
Hmm.
how over here we did the revert, like we did the moles on top and the grams on the bottom because
Yeah,
we,
because we want in moles. So whatever you want
yeah,
is the one on top.
yeah, whatever you want to cancel will be on the bottom, right?
Yeah.
Okay, so then this would just be,
So then this cancels.
uh,
Mhm.
yeah, so we want to do, so this is 9. We can turn, this into 1/1, but yeah, it'll be 9 times the 27, right?
Mhm.
And the easy way to do this is I would do 10 times the 27, which is 270,
Yeah.
and it'll just be a little less than that.
Yeah.
So,
So 9 moles of aluminum would be around 270 grams.
oh, so 10 moles would be that much?
Yeah.
Um, uh,
Well, I said around, like
mhm,
around that
yep.
range.
And we wanted 9 moles, so it'll just be a little less than the 270.
Yeah. So
So,
less than 270.
yep. So 240 would be our closest, right?
Yeah.
Good.
And that's the correct answer.
Hmm.
All right. Awesome.
Hmm. So yeah, be very, very comfortable with doing these types
Yeah.
because they'll ask you in a lot of different ways. Like yeah, so this one is just asking you like how to balance the reaction.
Yeah.
So what do you think?
Okay. What did I exactly do here? I think I just gave up on that for no reason. Let's see. Aerobic cellular respiration is described by the imbalanced chemical equation below. What are the coefficients of the balanced equation? Well, C6H level 6 plus O2 equals 6H2O. I mean 6CO2 plus 6H2O. Plus ATP, which is energy.
Mhm.
So it's obviously one here. Oh,
Mhm.
yeah, plus 6O2 equals 6HCO2 plus 6H2O.
Mhm.
So yeah,
Yeah. So it
that
seems
was
like you
stupid
like had that remembered, but I just want to make sure that you're able to do it like, if you had to do it,
of me.
like, you would see like, okay, there's 6 carbons here
Mm-hmm.
and there's 1 carbon here, so you want to put that 6 here to get 6 carbons on left and right.
Yeah.
And then I would do the hydrogen. So there's 12 hydrogens here and there's H2O here. So if I put a 6 there, that would give me 12 hydrogens, right?
Mm-hmm. And then that would also give you 6 oxygens as well. You have 8 of them, so
So okay, then we would have 6 oxygens and then 6 times 2 or 12 oxygens here
mm-hmm.
to give me a total of 20 um oxygens, right? So 6 oxygens from the H2O and then 12 oxygens from the 6 CO2. And
Yeah.
then
You
here,
mean 18, right?
what's up?
It would be 18 oxygens from this.
Yeah. So yeah, what did I write? Oh yeah, yeah, that's the oxygens. Yeah, so this would be
Mhm.
18 oxygens on the right. And then here we have 6 oxygens, and then 6 times 2, 12. So 6
Yeah.
plus 12 would give me 18. So 18 oxygen on the left, 18 on the right. So yeah.
Mm-hmm.
Okay.
Sounds perfect.
Yeah, you can, yeah.
Eh, oh boy. I don't know, erase it. How do you do? Oh, clear. Got it. Okay. Yeah.
Okay, yeah, this is like a naming one.
Uh, yeah,
Okay.
chlorate. Yeah, for chlorate. 104 minus ionic barium sulfate.
Hmm.
Molar mass is an ionic salt used as a contrast agent in X-ray diagnosis of JW. Yep, I know. I've drank it so many times.
Oh.
Uh, the KSP for this inorganic compound is 1.1 times 10 to the negative 10. Solubility of barium sulfate in pure water.
Hmm.
Okay.
So, so for anything with a K, capital K,
Mm-hmm.
that is derived from something called the law of mass action. So if we had, let's say, a chemical reaction like this, where the lowercase letters indicate the coefficients
Mm-hmm.
and the uppercase letters indicate the element or the compound or molecule or whatever,
Yeah.
the law of mass action would be the products, like the concentration of the products, and whatever the coefficients are, we use that as an exponent.
Mm-hmm.
So products, and then over the reactants, like this.
Mm-hmm.
And that's the law of mass action. So this is essentially for all the K stuff. So like you could have KEQ, KW, KA, KB, KSP,
Mm-hmm.
right? So for KSP, so if we think about the barium sulfate, right? And they're asking about how soluble it is in pure water. Let's think about that, right? So barium sulfate, what would that turn into in water?
And water would dissociate into barium, and then
What does the
um, uh,
order?
yeah, barium 2 plus,
Mhm.
um, S 2 minus,
Mhm.
and then O 4 2 minus. Oh, or SO 4 2 minus. Yeah,
Oh yeah.
because
Because
it could be sulfate ion.
yep, it's a sulfate ion. Good. So okay, so now we want to put it into something like this. But the thing is, if we have a pure substance,
Mm-hmm.
because the stuff in the brackets are molarity, right? Or concentration.
Yeah,
A pure substance would have to have a concentration of like 100%, right?
yeah.
So we don't include any pure substances in our calculations. So that means because the barium sulfate here is because when you're doing KSP, you're taking a solid and you're putting it in water and dissociating it, right? So
Mm-hmm.
you don't want to include, so I'll just even write that. You don't want to include like solids or liquids.
Yeah.
You can include aqueous because that will give you a concentration that isn't 100%. And you can use like gas, which can also be because you can mix gases, you can mix aqueous stuff, right?
Mm-hmm.
But a solid or a liquid would be pure, a pure substance. So it won't have a like it'll have like a concentration of like 100%, right?
Yeah.
So okay. So to set up this KSP here, it would just be the product, so barium 2 plus, and there's only one of them, so exponent will just be 1, which is the same as not even having an exponent. And then sulfate 2 minus,
Mm-hmm.
and normally the denominator will be where the where the reactants are,
Yeah.
but the reactant here is solid, a pure substance, so we're not including that. So right here, we have the KSP written out.
Yeah.
Okay, now to go from KSP to like it's called molar solubility. Um, well, we have three options. So for instance, let's say we have MX, like whatever solid, that would turn into like M plus and then X minus. Like for instance, right?
Uh-huh.
Now to turn this into molar solubility, we substitute X for each of these. So this would mean that you multiply these two. So this would mean you would get an X squared value. Now that let me show you that in comparison to the two other things you might get. If you get MX2, that would dissociate into M plus 2X minus, right?
Mm-hmm.
So this would mean this turns into the X, this turns into the 2X. Now this is a little tricky, but it's going to be X times the 2X. And remember, the coefficient we use, we turn it into an exponent. So the coefficient here is 2. So this becomes squared. Okay.
Okay.
Now, if we did the math here, this would then be X times So the 2x inside, if we squared that, that would be 4x squared, right?
Mm-hmm.
So now it's x times 4x squared, which is what?
Um, Wait, x times 4x squared.
Mhm.
Sorry.
Yep.
Uh, it would just be 4x squared.
4x squared times x.
Yeah,
So what's x squared times x?
2x squared.
So let's think about,
X cubed.
yep.
Oh, okay.
Yeah, if you're
Oh,
multiplying
yeah, yeah, yeah.
4x cubed, good. And then the last type of thing you might see is mx3, right?
Yeah.
That'll be m plus 3x minus. So then this would be x times 3x cubed, right? So what's the 3x cubed? Just like 2x squared is 4x squared,
Mm-hmm.
3x cubed. So like, what's 3 cubed?
27.
Hmm. And then x cubed is x cubed times x
Mm-hmm.
plus what?
Um, X to the fourth.
Yep.
Yes.
Okay. So these are the three types of things that it might give you. Um, so like, for instance, if it was like barium hydroxide, right? Whoops. That would be like an example of like MX2.
Mm-hmm.
And then like maybe MX3. Trying to think of something that could be. But it would be something like, with something on the left and then three of the things in the middle. I'm just trying to think of like a 3+ charge thing, but that would be like this thing in the middle. Yeah, maybe iron. Oh no, sorry. Lead iodide. That would
Mm-hmm.
be PbI3. So that would be an example of this thing over here.
Mm-hmm.
But yeah, we just have barium sulfate, so that's just equal amounts of each. So that's just going to be the x squared.
Mm-hmm.
So here we would put, so the KSP is 1.1 times 10 to the negative 10, and that's equal to x squared. And then we have to solve for just the solubility of the, oh, well, the solubility of the barium sulfate in pure water. So we just want to solve for the x here. So what we can do, so we want to solve for the x here, right?
Mm-hmm.
So what do we do first? So if we want to get x squared to be x, we would want to take the square root, right?
Oh, okay. Yeah.
But the square root in terms of so okay, for instance, right, x squared, if we took the square root, that would be x, right?
Mm-hmm.
But it's kind of hard to do that for, the square root of 1.1 times 10 to the negative 10. So we
Yeah.
can figure out if we could take the square root of something by using an exponent, right? So
Okay.
if we had, because if x squared, the square root is equal to x, and that's x to the
Mm-hmm.
first power, that would mean that if we had the x squared, we would take it to a certain exponent that would give us x1. So what if we took it to the power of 1/2?
Mm-hmm.
So I want to quickly just make sure. So for instance, if I have x to the a power times x to the b power, what will our answer be?
XAB.
So if you're taking an exponent to a certain power and you're multiplying it by an exponent to another power, you
Mm-hmm.
add the exponents.
Mm-hmm.
Okay. Now, if you do x to the a divided by x to the b, you would subtract the exponents.
Yeah.
And then lastly, if you take an exponent like x to the a to the power of another exponent,
Then you.
that's when you would multiply.
Mhm.
Okay.
All
So
right.
so if we have x squared and we take it to the 1/2 power,
Mm-hmm.
we would have x like with 2 times 1/2, right?
Mm-hmm.
Which is what? 2 times 1/2.
2 times 1/2 be 1.
Yep. So if you wanted to do a square root, you would take something to the power of 1/2.
Okay.
Okay. And likewise, if you want to do a cube root, you would take it to the power of 1/3. Okay.
That-
So for this over here, we want to take both sides to the power of 1/2, right?
Okay.
So the x squared to the power of 1/2 is just going to be x, right?
Yeah, and then 1.1 would be, well, we just do minus 10 to the 5.
So so for
I
this,
mean, minus to the minus 5. So
yeah,
negative.
because because basically 1.1 times 10 um to the negative 10, right? If
Mm-hmm.
we took this to the 1/2 power, it would be, well, 1.1 to the 1/2 power, but 10 to the negative 10 to the 1/2 power is what?
Just 10 to the negative 10 to the 1/2. Wouldn't that just cancel out?
So let's try that. 10 to the negative 10 to the 1/2
That's
power.
0.5?
Um, so what do we do to the exponents?
Oh, we multiply them.
Yep.
So 10 to the negative 5.
Yeah.
Got it.
So yeah. So the 1.1 we can kind of leave as 1, right?
Mm-hmm.
So we would just get something like so like x equal to, let's say, 1 times 10 to the negative 5, right?
Mm-hmm.
And so that'll be our answer, right?
Got it.
Yeah.
Okay, understood.
So yeah, this type of question could get tricky, especially with if they gave you something like this. Because if you gave you something like this, then we would have to take the cube root. And if they gave you something like this over here, you would have to
Mm-hmm.
take the, I guess, the fourth root, whatever
Yeah.
it's called. So you would just do 1/4 for that, and then for the cube root, 1/3.
Yeah.
And yeah, and then remember these exponent rules over here. So you'll
Got it.
be using them all.
Yes.
All right, so this one makes sense.
Yes.
Okay.
All right. And I think this we're gonna leave it off for today.
Oh,
Uh,
just that one, or do you want to do one more?
let's see. All right, we could just do this one and then we'll call it.
Sure. So lithium chloride.
Oh, yeah. All
Lithium
right.
chloride is a soluble salt. Um, which of the following statements regarding this ionic compound is correct? So I see. Okay. So let's talk about the water molecule.
Mm-hmm.
Do you remember what it looks like?
Wait, what? In water?
Oh, just the water molecule itself.
Uh, well, yeah, H2O. So, it's a oxygen double bond. I mean, bound to 2 hydrogens.
Would it look like this?
No, because it's not an ether.
Uh,
Well, actually, yeah.
so let's see, right? So, we could always start off by drawing Lewis structure. So like
Mm-hmm.
1, 2, 3, 4, 5, 6, right?
Yeah.
So so it has 6 valence electrons, which means that these two single ones can form bonds with hydrogen,
Yeah.
like that. However, we have these lone pairs here. And lone pairs repel bonds more than another bond would.
Yeah.
So, so this is like a linear shape, right?
Mm-hmm.
But it won't be a linear shape because it has these lone pairs. It will be a bent shape because the lone pairs will push these hydrogens together,
Mm-hmm.
right? And so water, I guess is polar, right?
Yeah.
So if water looked like this, it wouldn't be polar, right? It would be like a symmetrical linear structure.
Mm-hmm.
But that's why it won't look like that. It would be bent like this.
Yeah.
And if it's bent like this, uh, it would mean that it's polar. And if something is polar, in other words, it means that it has partial charges.
Yeah.
Okay. Now, so now let's think about what partial charges it would have. So whichever atom is more electronegative,
Mm-hmm.
electronegativity is how much something likes electrons, how much it can pull electrons towards itself. So
Uh-huh.
that means that if we drew out so oxygen is more electronegative than hydrogen, right?
Mm-hmm.
So hydrogen has its electron density pulled towards the oxygen like that. Whoops.
Yeah.
Like, oops. So like that. So that means
Mm-hmm.
that if it's polar, it will have a partial charge.
Yeah.
And since oxygen is electronegative, it'll have a partial negative charge.
Negative charge. Oh, okay, never mind.
And
I
hydrogen
see
will
where I'm
have a
wrong.
partial positive charge. So you were sort of close here, but the oxygen is electronegative and will have a partial negative charge.
Yeah.
Okay. And um, so it would be this one because you have, so first of all, we want to see partial negative oxygen. So we see partial negative oxygen here, partial positive oxygen here, which is wrong. So that's out.
Mm-hmm.
Partial positive hydrogen here, which is fine. And then we want to see, okay, what would react or what would be attracted to what, right?
Mm-hmm.
So if this says partial positive hydrogen, lithium plus wouldn't be attracted to partial positive, right?
Yeah.
That's out. And then we have these two. Chloride, which is negative, wouldn't be attracted to partial negative, right?
Mm-hmm.
Opposites attract, so that's out. And that only leaves C. And this makes sense because we have positive lithium ions attracted to partial negative oxygen atoms.
Okay.
Okay. So for this, we want to first be able to understand that water is polar. And why is water polar? Because it has those lone pairs,
Yeah.
which gives it a bent structure. And then you want to consider, so if it's polar, it means that there are partial charges. So which charge is, I guess, which partial charge is what, right? So
Yeah.
whichever is more electronegative will be partial negative. Whichever
Mm-hmm.
is less electronegative will be partial positive. Another common one you would see a lot is a carbonyl group like this.
Yeah.
So this carbon here is double bonded to this oxygen, right? Now, what's more electronegative, oxygen or carbon?
Oxygen.
Yeah. So this would produce a polarity in this direction, right?
Mm-hmm.
So there would be partial charges. So what would the partial charge be on this carbon?
It would be partial positive, while on
Good.
the oxygen it's partial negative.
Good. Good. Good.
Yeah, I get it now.
Mhm.
All right.
All right, awesome. So, uh, I would say continue like to review all of these.
Mm-hmm.
Um, all of like the Jack Weston content diagnostic stuff that you did, like
Yeah.
review them and see if it makes sense. And whichever ones still don't make sense, when we meet next, we can go over them.
Okay.
And when do you want to meet next?
The Thursday, the 21st.
Okay. Let's see. Do you want to do 3 p.m. again?
Yeah, 3 p.m. works.
Okay, got it.
All right. So then I'll see you then, all right?
All right. Take care. And yeah, I'll see you then. Okay. Take
All
care.
right, see you then.